Welcome to this Brainline exclusive video of a discussion of power in electric circuits. This is a topic which you can expect to find in any grade 12 paper, be it a DBE or an IEB exam. It's very important to remember that the brightness with which a bulb glows is related to the power. In other words, when a question is asked in which you are asked to explain how the brightness of a bulb will change in a specific circuit, you always have to refer back and answer with relation to power. Now the formula which we had for power was P for power equal to V times I, where P was the power in watt, V was the potential difference in volt, and I was the current in ampere. Now, of course, we always have to firstly start off by looking at how the bulbs have been connected. The bulbs could possibly have been connected in series, or alternatively, they could have been connected in parallel. And that's always where we're going to start. If we have bulbs that have been connected in series, we know that the current which flows through one of the bulbs also flows through the other. In other words, if this bulb was labeled resistor 1, this one was labeled resistor 2, then the current in resistor 1 would equal the current in resistor 2. In other words, the current would be the controlled or the constant variable. On the other hand, if we had resistors connected in parallel, we would have two light bulbs, as an example, connected in parallel, and we know that the current that flows in the series part of the circuit, once it gets to the parallel part, would split. Some would flow through the top bulb and some through the bottom. Let's say that these two resistors were called resistor 3 and resistor 4. The current is definitely not constant. We know that resistors, or in this case bulbs in parallel, are called current dividers. On the other hand, if I were to consider the potential difference, if we were able to connect a voltmeter across the whole parallel network, or alternatively, connect a voltmeter across only a part, so across only R3 or across only R4, then this voltmeter would have the same reading. In other words, we know that in series, the potential difference across each of the resistors equals the potential difference across the parallel network, and therefore the voltage or the potential difference is the constant variable. We've also worked with Ohm's law. In Ohm's law, we learned that the resistance of a resistor, in this case a bulb, is equal to the potential difference across the bulb divided by the current flowing through the bulb. Now we can of course rewrite this formula, R equals VI, and it could possibly become V equals IR. There I've kept V as the subject of the equation, or of course we could also change it so that I became the subject of the equation, in which case it would be V over R. Now the brightness is always going to be related to the resistance of the combined resistors, and we're going to play around with the resistance of these resistors and then determine what the brightness would be. Our next step will always be to try to change the equation for the power, in other words, this specific equation, so that we are left with P for power, R for resistance, those are the two that are related, and then the third variable being the one which is constant. In other words, in the series circuit, I would be trying to get a formula which had in it P for power, R for resistance, and then also I, because we know it was constant, and we could then deduce a proportionality. For the parallel set, we would look for a formula which had the P for the power, R for the resistance, and then that which we know is constant, in other words, the potential difference. Now to do that, it means that I will go back to this original formula P equals VI, and I will rearrange it in such a manner that for series I would be able to eliminate the V. To do that, we'd start off then with the equation P equals VI, and I want to eliminate the V, so I'm going to be looking for a formula in which the V would be eliminated. In other words, this is the formula I'm going to put in, and I'm going to be replacing the V in the formula with the IR. So it becomes IR multiplied by the I, which was already there, and therefore the formula is I squared R equals the power. We're going to do the same thing on the parallel side. This time we want to eliminate the current because all we want to have is power, resistance, and potential difference. So to eliminate the current, it would mean that we would have to start off with the original equation, which was P equals VI. We want to eliminate the current, so we're going to use this formula so that I can replace V over R in the place of I. Therefore, V in the place of I, I'm going to say V over R. And when the V and the V are multiplied, it becomes V squared over R equals power. So for the series circuit, we will work with P is I squared R because I is constant. And for the parallel circuit, we will work with P is V squared over R because V is constant. In the first part of this video, we looked at how we could determine which formula to use to help us to understand how the brightness changes or how it compares for two or more resistors which have different resistances. In this example, I'm going to be having two bulbs in series. The one is resistor 1 with a resistance of 5 ohm and then resistor 2 with a resistance of 10 ohm. We saw that P equals VI gives us P, the brightness or the power of the bulb, and that we would use V equals IR from Ohm's law to end up with the formula when we were working in series for P equals I squared R. Now the relationship is always between brightness, and we said that brightness is always related to power. So the brightness we need to find by looking at the P, and then secondly the R is the one which is changed because we had a 5 ohm and a 10 ohm light bulb, and we want to know which is brighter. As soon as we want to know the relationship between two variables in an equation, we always try to take the formula which has those variables as well as a constant variable, and we rewrite the formula so that the two which are related, the P and the R in this case, are on the same side of the equal sign, and that variable which is constant is kept on its own. So to keep the constant on its own, I would need to bring the R to the left hand side. It's multiplied on the right, so to bring it to the left, the formula would relate to P divided by R equals the I squared, which we know is constant. From our laws of proportionality, we know the two variables which when divided are equal to a constant are directly proportional. In other words, power is directly proportional to resistance provided that the current is constant. In other words, provided that we are working with bulbs which have been connected in series. So what does a direct proportion mean? Direct proportion means if the one variable increases, then the other increases, or if the one has a high value, so does the other. In other words, should the resistance increase, I can read it this way back then, the the power would increase. If the power is higher, the resistance is higher. So let's come back to these two resistors. Because we can see that the power is related to the brightness, and we're looking for the brightness, we're going to go back, we're going to look at the resistors, we're looking at their resistance, and we can identify that for resistor 1, the resistance is lower, while for resistor 2, the resistance is higher. From the direct proportionality, we can therefore deduce that the power for resistor 1 is less and the power for resistor 2 is more, because remember, we are relating those two to each other, and we know that there is a direct proportion relationship. The same is going to happen on this side. In other words, very simply, the 5 ohm bulb is going to be the dimmer of the two, and the 10 ohm bulb is going to be brighter. The reason, if I was asked to explain, would be that in series, the power or brightness is directly proportional to the resistance. Therefore, if the resistance is lower, then the brightness or the power is lower as well. Let's consider what would happen if we had bulbs connected in parallel. Let's consider having R3 and R4, again of 5 ohms and of 10 ohms. They're connected in parallel, and we know that power, brightness, equals VI, and from Ohm's law, we've deduced that I equals V over R. Now, I've chosen to make I the subject of the equation because V is the one that we know is constant, so we're actually trying to keep the V, and we're trying to eliminate this I which is not constant because the current split when the bulbs were in parallel. If I were to therefore replace the I in P equals VI, it would become P equals V, and then replacing it with, instead of the I, which is that I, the V over R, it would therefore become times V over R, or then V squared over R. From P equals V squared over R, we're once again going to try and rearrange the equation so that that which is constant remains on one side of the equation, and the two factors which we're trying to relate, P for the brightness and power, R for the changing resistance, are then kept on the same side of the equal sign. This means that I'll have to bring the R across. It's going to come and stand up. It was divided on the right. It's going to be multiplied on the left. In other words, we're now going to have P times R equals V squared, where the V squared is the constant variable. Now, from the theory of proportionalities, you should know that if we have two variables which are multiplied, like the P and the R, to form a constant value or to give a constant value, then those two variables would always be inversely proportional. We therefore know that P is inversely proportional to R. Now, what does inverse proportion mean? Inverse proportion means that if the one variable, for example P, is high, then it tells us that R has a lower value. They're inversely proportional. Direct proportion, same. It would imply that a bigger value of the one is a bigger value of the other, relates to, whereas inverse proportion means that a high value and a low value relate to each other. In other words, coming back over here, let's go and look at the resistors that we have. Let's go and look at the power. The resistors were a 5 and a 10 ohm respectively. In other words, the 5 ohm has the lower resistance, the 10 ohm has the higher resistance. This then tells us via the inverse proportion that the power for the 5 ohm resistor is higher and that therefore the 5 ohm resistor shines more brightly, while the 10 ohm with the higher resistance has the lower power and therefore is more dim. To summarize, we can therefore remember that for series circuits, we're looking at power and resistance being directly proportional. The higher the resistance, the brighter the bulb. For a parallel circuit, inverse proportional relationship between power and resistance. In other words, the higher the resistance, the more dim the bulb. I trust that this has contributed to your understanding of this rather important topic and suggest that you ensure that you will be able to answer both short questions in the multiple choice as well as explanatory questions in the longer questions. Good luck to you all.